So far we have seen that how a Turing machine works, and what is the instantaneous description of a Turing machine, how to represent the working of a Turing machine using a transition diagram, transition table. And we have seen two examples that when a language is given, how we are going to implement that using the transition diagram and transition table. Now all these were under the basic Turing machine concept. What is the difference between basic and non-basic, we will see in the slides. Now that here we are going to visit some one new concept that which is covered under this extension to the basic Turing machines, that if we increase the number of tapes in a Turing machine, that how it is going to function. And at the end of the day we will say that multi-tape Turing machine and single tape Turing machine are equivalent in functioning. Okay, that is our motto in this lecture. Fine. So what is multi-tape Turing machine? Right, so here the device will have a finite control, similar to that of your one tape Turing machine, and some finite number of tapes. There in one tape Turing machine there was only a single tape. Here we will have some finite number of tapes. Okay, that should be more than one, but it has to be finite, right? Now each tape is divided into cells. We know that each tape is divided into different cells, and input string remains there, and rest of the cells are filled up with blanks. Here the same thing will also occur. Here every tape will be divided into cells, right? And each cell can hold any symbol of the finite tape alphabet. We know that whatever the input alphabets are, we have to place that in the finite in the tape, in the cell of the tape, right? So as in the single tape TM, the set of tape symbols includes a blank and has a subset called the input symbols, of which the blank is not a member. There was the concept of blank symbol, we know that. And the set of states includes an initial state and some accepting states, right? So here again it will have an initial state and some accepting states. We know that initial state is 1 and accepting states or final states can be more than 1. To begin with this, initially the input, that's the finite sequence of input symbols, is placed on the first tape. So just we will visit the diagram in later slides. There you can see that there will be a multiple number of tapes, obviously finite number of tapes, and the input which we are going to process will be placed in the first tape only, right? It will be placed in the first tape, and it will be a finite sequence, right? And all the other cells of all the tapes hold the blank. So initially only the first tape is going to contain my input symbols or input string which we are going to process, and rest of the place in the first tape will also be filled with blank, and the other tapes will also filled with blank, right? The finite control is in the initial state. Means we know that the initiation of any processing begins from the initial state, and so the finite control head is going to place over there only, right? The head of the first step is at the left end of the input. Fine. Okay, so the head of the first step is, means since we process a string from starting from my left hand side to the right hand side, so the head is going to point there only, and all other tapes heads are at some arbitrary cell. So since you see that all the other tapes other than the first tape is containing only blank symbols, so where the tape head is for those tapes, that is it has no meaning to consider that thing, right? So we are considering only the first tape in this case where my input strings are there. For rest of the tapes it is having only blank symbols, so fine, the head can be anywhere else. So let us see the diagram. You can see this is a diagram, the finite control, and you can see that there are three heads here. Since we are just depicting three tapes here, it can be more than that. So first initially the head is in the first tape in the second cell, and the second tape it is also pointing to somewhere, and in third tape it is also pointing to somewhere. So in case of second tape and third tape, the head can be anywhere. We are not considering that, but for the first tape, since the first tape is including all the input symbols which we are processing, so the tape head should be means we have to consider where the tape head is locating, right? So a move of the multi-tape TM depends on the state and the symbol scanned by each of the tape heads. Obviously, we are considering for the beginning that all the tapes other than the first tape is consisting of the blank symbols only. But after certain number of executions, the situation may be like this, that first tape is processing something, second tape is processing something, and third tape is processing something. So we know how a move is determined. We know that where, in which state the Turing machine's head is pointing and which symbol it is scanning, right? We know that the idea of Turing machine, it consists of the state in which it is lying and the symbol which it is scanning, and it gone, and the output is it will move to a new state. It may be the same state as also. It will move to a new state and will change the change the input symbol which is lying in that place to another value, and it will determine the direction where it needs to move. It may be left, it may be right, right? So the same thing will occur here, right? So in one move multi-tape TM, what it does we will see one by one. The control enters a new state which could be same as the previous state, right? So this is very similar to the single tape machine. Now on each tape a new tape symbol is written on the cell scanned. Any of these symbols may be the same as the symbol previously there. So you can think, you can see that we are just learning, or we are just getting to know that all the same things, but in a form that in previously we have considered all this thing with respect to a single tape. Here we are considering everything with respect to multi-tape, right? So here on each tape a new tape symbol is written on the cell scanned. So here in the previous case what we have done, so whichever symbol we are scanning, we used to write some different symbols, or it may be the same symbol in that place. So the same thing will be done for the multiple tapes as well. Okay. Now next, each of the tape heads makes a move which can be either left or right or stationary. So see here a new thing we come to know, that in case of single tape machine, the tape head either moves left or moved right. So here, since we are considering multi-tape, so there may be situation, say in our diagram there is a movement for the tape 1, so say it is moving left, for the tape 3 it is moving right, but there will be another situation for tape 2, it is not processing anything, not doing anything, so it is not going to move anywhere else, so it will remain stagnant, so it will be stationary, right? Fine. So now we will see that equivalence of multi-tape and one-tape Turing machine. So, since see, if we can prove this one, that this multi-tape and one-tape Turing machine equivalent, then we don't have to worry about the concept of multi-tape anymore, right? So how we are going to prove it? We have seen. We have not gone details of the recursively enumerable languages so far, but in our previous class we have just introduced a single slide at what a recursively enumerable language is. For the time being, we will let that whatever the languages a Turing machine accepts, those class of languages are termed as recursively enumerable language, right? So if one tape is accepting the languages which we termed as recursively enumerable languages, we will learn about details about recursively enumerable language in our next lecture, or 2 to 3 lectures later, right? So here, if one tape Turing machine, we know that it is going to accept only recursively enumerable language, then if we can prove that multi-tape Turing machine are also accepting recursively enumerable language, then we can say that both of them are equivalent. So we will try to prove it. Fine. So let us see how we are going to just compare these two. So we are supposing here a language L that needs to be recursively enumerable is accepted by a k-tape Turing machine M, right? A k-tape Turing machine M, there are k-tapes, say means in the previous we have seen that multi-tape, so multi-tape means how many tapes are there. Here we are assuming that value as k, right? So we simulate M with one tape TM N. Here we are considering one tape TM as N and multi-tape TM as M, right? So here we are going to simulate this multi-tape Turing machine using a single tape Turing machine. Okay, how we are going to simulate it? We, instead of assuming k tapes Turing machine, we are assuming it as it is having 2k tracks. Now why 2k, right? Why not k? You can see here that in the second line of the diagram it is a1, a2, ai, aj, anything, and in the first there is one x, in the third there is one x, and in the fourth there is b1, b2, bi, bj, right? So what it is doing here, the half of the track, total number of tracks, whatever the available number of tracks are, so the half of the tracks holding the tapes of m, right? So which are those tracks? Just see the second one. Say it is the first tape of my k-tape Turing machine. Fourth is my second tape of k-tape Turing machine, right? And what are the first and third row or third tracks are doing? They are holding the marker. Marker means what? That indicates where the head of the corresponding tape of m is correctly located, right? So if you can if you just remember the previous diagram, you can see that for each and every tape there were a finite head separately, but if we want to simulate this multiple concept into with a concept of single tape Turing machine, so we will have only single header pointer. So what we have to do? We have to keep a marker, otherwise the value will lost, right? So we have to store where the finite control of first tape is, where the final control of second tape is, where the finite control of kth tape is. That's why for each tape we need two tracks. One track is going to hold the location of the head, and second tape is going to hold the content of the tape, right? That's why 2k. Okay, now for simplicity we are assuming the value of k as 2. Okay, here you can see that the second and fourth tracks are holding the contents, and the track 1 and track 3 are holding the control. Okay, so we have already seen it. Now see, to simulate a move of m, n's head must visit the k head markers, right? So k head markers it has to move because k number of tapes are there. So n will not get lost anywhere, so since the header marker is there, right? So it has to remember it. That's why we are using one marker. Now after visiting each head marker and storing the scanned symbol in the component of its finite control, n knows what tape symbol are being scanned by the m's head, right? So it is already storing it. So whatever m's head is scanning, say for the first tape, whatever m's head is scanning, for the second tape, whatever m's head is scanning, everything is known to n because it is going to store in the x values of each and every track, right? First track, third track, fifth track, in this fashion. So n also knows the state of m which it stores in n's own finite control. So since it can study where the head of each of every tape of m is locating, so it is also know which state it is now, right? So which from initial state where it has gone, from that state where it will go, right? So everything will be known to n. Now n now revisits each of the head markers on its tape, changes the symbol in the track representing the corresponding tapes of m, and moves the head markers left or right if necessary, right? So if it knows where for each and every tape whatever m is doing, so it will also know that for this state and for this input symbol whatever output my m is going to generate for each and every tape, right? So n is going to change that place also, right? So changing means for each state and input symbol, whatever the symbol it is going to write in that place. So that can be done by n as well. So finally n changes the state of m as recorded in its own finite control. At this point n has simulated one move of m, right? So in this fashion n has simulated only one move of m. So in this fashion it can simulate all the moves, right? So we select as n's accepting state as all those accepting states that records m state as one of the accepting states of m, right? So if it can learn that whatever the accepting states for each and every tape of m is, if we accumulate everything, so that will become the accepting states for n, right? Thus, whenever the simulated m accepts, n also accepts, and if n does not accept, that means m has not accepted. So that means we are successfully converted a multi-tape Turing machine to a single one tape Turing machine, right? We have mimicked everything whatever a m tape or k tape Turing machine does. Now we will see one more theorem. So it is easy to understand, still we are going to explain, right? So here what it is doing, that to simulate n moves in k tape from what is the time consumed, right? So we have seen that for one move, we have seen the one movement it can simulate, so we can easily say that it can also simulate the n number of movements of m tape. So how many, whatever the time complexity is, we will prove that to be order of n square. How? So you can see that since for k tape Turing machine, how many number of tracks should be there? 2k, because for each and every tape there should be 2 number of tracks, right? That's why after n moves of m, the tape head markers cannot have separated by more than 2n cells, because for n cells there can be maximum of 2n spaces in between. It cannot be more than that, right? Since for each we are allocating 2, so for n we were going to allocate 2n only, right? So if n, that is my one tape Turing machine, starts at the leftmost marker, it has to move no more than 2n right cells, right? So if the movement is from left side, so how many maximum number of movements it has to cover up to move towards the right? 2n, right? Now similarly, if it has to move left, how many maximum number of movements it should have to come out of? That is 2n as well. So from left to right it has to cover maximum of 2n, from right to left it has to cover maximum of 2n, right? Plus, why 2k number of moves? Because for each cell there, since we are just we are simulating k tape machine, so from if it has moved to one head, right? So if it requires, means for jumping of n number of cells, it needs maximum of 2n towards the right, and for again from right to left it needs 2n. Now doing plus 2k moves it needs, because from one direction it may that marker has to cover up again 2k moves, because there are k number of tapes. For each tape there are how many tracks we are incorporating? For each tape we are incorporating 2 tapes, right? That's why 2k moves it needs, right? And cells, why 2n? Because for each tape, since there are n number of cells, but here we are incorporating 2 tapes for each tape of multi-tape machine, that's why n for one tape and n for another tape, that's why 2n from left to right, and from right to left for cell movement it is again 2n. But for each track, right, so for each of the movements from left to right there will be again 2k number of moves, because for k tape we need total number of 2k tapes in case of one tape machine, right? So if we convert everything like this, for first move, means for single move, so how many it requires? 2n from left to right, 2n from right to left, that is 4n, and that is number of cells, and track movement will be 2k, right? So 4n plus 2k. Now here k is a finite number. We have assumed that k is a finite number. So if we have to find out the complexity of this, it will be order of n. Now this is true for all n number of tapes. We have calculated this for a single tape movement. So if we consider all the n number of movements, right, so this is for one movement only. If we consider total n number of movements, so it is going to get multiplied with n, that's why it will be order of n square. Fine. This much for today. In the next class we will learn one more thing, that is non-deterministic Turing machine, and we will see that the deterministic Turing machine and non-deterministic Turing machine are equivalent. We are going to prove it. Thank you.